In this video, I'm going to look at enthalpy change of neutralisation. So on the board, I've got the classic neutralisation reaction between hydrochloric acid and sodium hydroxide, and that would produce sodium chloride and water. You can see underneath in red, I've written down all the ions present. It's separated them out. And now I've cancelled out the common ions on both sides, and I've got the overall equation that's taking place, which is simply the reaction between an H plus ion and an OH minus ion to form water. So the enthalpy change for this reaction is the same as the enthalpy change for this reaction. And that leads us to the definition for enthalpy change of neutralisation, which is the enthalpy change when an aqueous acid neutralises an aqueous base to form 1 mole of water. So what I'm going to do in the video now is I'm going to measure the enthalpy change of neutralisation, and I'm going to do it using a calorimetry experiment. So across the top of the board there now, I've got the 2 steps involved in the calculation that we're going to perform at the end of the experiment. And the starred information here is obviously this is the equation that we need to calculate the enthalpy change for. So step 1, Q equals mc delta T. That is going to tell us the amount of energy released. In this case, it's an exothermic reaction by the reaction that's going to take place in this polystyrene cup. So the M will be the total mass of the solution inside this cup. The C is the specific heat capacity for the solution, and delta T is the temperature change, so the difference between the initial and the final temperature. You can see the thermometers in these measuring cylinders. So I'm ensuring that the starting temperature of the alkali in this one here and in this one here is the acid, they're going to start at the same temperature, so that the temperature change that I measure is the temperature change that takes place in the reaction. Once we know the Q value, we can feed that into step 2 to find the enthalpy change. And just be aware that enthalpy changes are measured in kilojoules per mole, and the Q comes out in joules, so we need to turn the Q into kilojoules and then divide it by the number of moles. So you can see in red here, I've already entered some information. So I've got 25 cm³ of acid and alkali in these measuring cylinders at the moment. They are both the same concentration, and therefore the number of moles I'm using of each chemical is the same, so it's 2.5 times 10 to the minus 3 in both cases. Why have I done that? It's because these react in a 1-to-1 ratio anyway, so I'm going to use exactly the right number of moles. And of course, because of this 1-to-1 ratio, we're going to make 2.5 times 10 to the minus 3 moles of water. So we'll do the experiment now. I've transferred the acid into the polystyrene cup, and you can see the initial temperature of both of the solutions is 26 degrees Celsius. So we'll put the sodium hydroxide in, and we're going to measure the maximum temperature that we get. So I've given that a stir and allowed it to reach its maximum temperature. Not very exciting, I'm afraid. We've gone from an initial temperature of 26 degrees C to a final temperature of 26.6 degrees C. So we've got a measly 0.6 degree temperature rise. Now the reason for that, I'm sure you can appreciate, is the fact that I've only used 0.1 mole per decimeter cubed solutions of acid and alkali. So I'm going to do it again, but I'm going to change the concentration of the acid and the alkali to 1 mole per decimeter cubed. So you can see I've changed the chemicals. I've now got 1 mole per decimeter cubed sodium hydroxide, 1 mole per decimeter cubed hydrochloric acid, still use 25 cm³ of each. I've adjusted the information on the board, So in terms of moles now of H plus and OH minus, we've got 2.5 times 10 to the minus 2 now, instead of times 10 to the minus 3. So the moles of water produced is going to be 2.5 times 10 to the minus 2. My initial temperature is still 26, so I'll put the alkali in and we'll record the maximum temperature. And I can see already the thermometer is going up much more than it was before. And that's a lot more like it. We've got a final temperature of 32 degrees C, and so our delta T is 6 degrees Celsius. Step 1 of the calculation in blue there, Q equals MC delta T. The M, the mass of the solution, is the combination of these two 25 cm cubes. The density will be 1 gram per cubic centimetre, so 50 cm cubes is going to be 50 grams. The specific heat capacity I'm using is 4.18 and delta T is 6. So that's given me a Q value of 1254 joules, which is 1.254 kilojoules. And then step 2, to find the enthalpy change, it's minus Q over the moles, so that's the minus 1.254 divided by the moles of water produced. Remember, we've got to scale it up to what 1 mole would have given, so we're dividing by 2.5 times 10 to the minus 2, and we're getting an answer of minus 50.2 kilojoules per mole. We were a little bit below the data book value of minus 57.9 kilojoules per mole, and the obvious reason for that, I've put this back in the middle, is heat loss. Obviously we're not going to get the data book value because we've got a lot of heat loss taking place with this apparatus set up. Obvious improvement to get a bit closer to the minus 57.9 would be some form of lid on there and improved insulation for the calorimeter. We'll just finish by looking at some other acids now. So I've got 3 acids there, nitric, sulfuric and ethanoic. Again reacting with sodium hydroxide. So have a think about how would their data book values for the enthalpy change of neutralisation compare with that of HCl, which remember was minus 57.9. The first thing we need to appreciate is the equation, the overall equation that's taking place in all 3 of these reactions is exactly the same. And it's the reaction we had before on the board, where we had H plus OH minus giving H2O. You can see on this one, the sulfuric acid one, we've got 2 H pluses from the H2SO4 and 2 OH minuses from the 2 NaOHs, making 2 waters. But you can see because the 2 is common to all of those, we can cancel that out. So it's still the same reaction. And ethanoic acid, again, H plus OH minus gives H2O. So is the enthalpy change going to be the same because the reaction's the same? Well, the answer to that is yes and no. So think about which ones or one will be the same and which one or ones won't be the same. And the answer is the first 2 would be the same, and that's because these are both strong acids and so they fully dissociate. The ethanoic acid is a weak acid, and so that's going to give a slightly less exothermic value for the enthalpy change of neutralisation. And just to go into a little bit more detail for the last one, ethanoic acid we've just said is a weak acid. It's partially dissociated into its ions, hence the reversible arrows there. So to get the H plus ions to react with the OH minus ions, we've got to effectively break this OH bond, and that's going to require some energy, and so that's going to eat into the enthalpy change value. So that's why we get slightly less energy shown.